Welcome to the second part of the problem-solving session for Chapter 28. And we'll begin where we got cut off because of some technical difficulties. We were attempting to calculate the value of R2345, and we were writing down 1 over 10 ohms plus 1 over 5 ohms plus 1 over 25 ohms, and we get a common denominator here of 50 ohms, and therefore we have 5 plus 10 plus 2, which gives us 17 over 50 ohms. Therefore, R2345 is equal to 50 ohms divided by 17. And if we would like to write this as a decimal, 2.94 ohms. Well, we're not done yet because we were asked to determine the total of R1, 2, 3, 4, 5. In other words, R1 plus R2, 3, 4, 5, since they are in series. And so our R total works out to be 10 ohms for R1 plus 2.94 for R2, 3, 4, 5. So 12.94 ohms, or 12.9 ohms in 3 significant figures. So we've answered the first part. The second part asked us to determine the potential difference across the points A, B. Well, if we come back over here, we notice that the potential difference across A, B is the same as the potential difference across R2, R3, R4, 5, and for that matter, a step that we did not show here, and that is, let's see if we can draw it. If we have the point A here, and R1 here, and our battery here, and the point B here, so we've got our R1 and our battery, and we come over here, what we have just done, R2, 3, 4, 5, before we added it to R1, is actually R2, 3, 4, 5. The potential difference across this combination of resistors is the same as the potential difference across AB. So we no more than have to find delta V 2345, and we'll have the value for delta V AB. So what can we do? Well, the first thing we note is that I total is the same as I1, the current through resistor 1, but it's also the same as I2, 3, 4, 5. In other words, the current through the combination 2, 3, 4, 5. And because of Ohm's law, we're able to get I total by taking delta V total, dividing it by R total, that is the R1, 2, 3, 4, 5, and we plug in our numbers, we get 1.93 amps. That means that we can go back to delta V 2, 3, 4, 5 and use Ohm's law again, this time I 2, 3, 4, 5 times R 2, 3, 4, 5. Well, we know I 2, 3, 4, 5 is 1.93 amps. We know R 2, 3, 4, 5 is 2.94 ohms. And the product gives us a value of 5.7 volts. Now, if we want to check whether this is correct or not, let's go to R1, in other words, delta V1, we know was equal to I1 times R1. Using I1 as 1.93, R1 as 10 ohms, we see we get a value of 19.3 volts. Does this agree with a total voltage of 25 volts? In fact, it does. Since R1 and R2345 are in series with each other, it should be true that V1 plus V2345 equals 25 volts, which indeed it does. Next problem. Oops. Let's come back over here. Oh, don't know what that is. Let's come back over here. All right, question 5 gives us a light bulb. In fact, it's a three-way light bulb, and it tells us that the light bulb supplies 75 watts of brightness, 100 watts of brightness, or 175 watts of brightness, depending on the position of the switch and what we select. We are therefore asked to determine the values of R1, R2, and the combination of R1, 2. Well, let's see. Oops, come back over here. Let's hope for no more technical crashes. We have R1 and R2 in parallel because if you look at the switch here, when S1 is closed but S2 is open, we have current that only flows through the 75 watt filament. When S1 is open and S2 is closed, we have current that flows only through the 100 watt filament. But when both S1 and S2 are closed, we have current which splits off. Some of it goes to the 75 watt filament, some of it goes to the 100 watt filament, and the combination of those two, since we have a split or a junction, makes these resistors connected in parallel. But we know, of course, that the sum of the power delivered equals P1 plus P2, which is, of course, 175 watts. So using the expression, because we're told that delta V total, what we get from the wall socket, is 120 volts, and these are in parallel, it should be true that delta V1 is equal to 120 volts, but so is delta V2, and therefore the combination of delta V1, 2. Using the expression P1 equals delta V1 squared over R1, since we know delta V1 and R1, we choose to use this form for power. We can solve for R1 equals delta V1 squared over P1, and that gives us a value of 192 ohms. We do the same for R2, delta V2 squared over R2, and we get a value of 144 ohms. Notice that the greater resistance has the smallest power because of the reciprocal relationship between these two. Well, how about R12? R12, which we can obtain as delta V12 squared over R12 squared, should equal, P12, I don't know why I said squared, P12, which is 175 watts, gives us a value of 82.3, is that correct? Ohms, yes. But if we want to double check that we did this correct, R12 should equal 1 over 192 ohms plus 1 over 144 ohms, taken the reciprocal, and if you put this in your calculator, hopefully you get 82.3 ohms, confirming that our work was done correctly. Next question. Here we are given a circuit with 2 resistors and 2 batteries, and we're asked to find the current through each resistor. Now, because we have 2 batteries, we have to resort to Kirchhoff's rules to solve this problem. Since there are no junction points, no place for the current to split, the current can only flow through the single loop, we don't use the junction rule, and in fact, we make note that the same current that flows through resistor 1 will flow through resistor 2. Now, in this diagram, they have started us off by saying assume that the current flows through the circuit so that when the current gets to R1, it will flow downward, making this the positive side and this the negative side. And when it flows through R2, it will flow upward, making this the positive side and this the negative side. But of course, I1 is equal to I2 is equal to I, so we don't have to differentiate the current as I1 or I2. I did here just to label it. So since we can't use the junction rule and we only have one unknown, the loop rule will satisfy will give us the equation that will satisfy the unknown current, the solution to the unknown current. And what we want to do here is to start by deciding which direction we want to take when we traverse this loop. In other words, what element, circuit element, do we want to start with? And do we want to add all circuit elements clockwise or counterclockwise? Now, this is going to be your guess, so I will give you a couple of seconds to decide which way you want to do this. Okay, your 2 seconds are up, and since you didn't say anything, I will decide for you. Just this once. We are going to traverse the circuit, the loop, in a clockwise fashion, and we'll start with the battery labeled E1. All right? Since we begin from the negative side of the battery, the negative terminal, to the positive, E1 is positive 6 volts, and I'm not going to write the unit here so that we don't end up with too many variables, or at least letters that appear to be variables. When I get to R1, notice that the direction of my loop is from the positive side of the resistor to the negative, or rather along the same direction as the current. And because I'm going from positive to negative, I have to subtract I times 8, or let me write it as 8I. And of course the I is I1, which is the same as I2, so I'm just going to leave it as I. Then I come over here to the second battery, E2, and I'm traversing from positive to negative, so this again will be a drop in potential, or a minus 12 volts. When I get to the resistor, I'm traversing from positive to negative, which means again I'm going to experience a drop, and I'm going to write that as a minus 10, because R2 is 10, times I2, or I, and I get back to the battery, so I'm going to set that equal to 0. Let's combine 6 minus 12 is minus 6, minus 8 minus 10 is minus 18I, set that equal to 0, and solving for I, we get 6 over negative 18, or negative 0.333 amps. What does it mean when the current is negative? Well, what it means is that the initial guess for the direction of the current was incorrect. In fact, the current flows through the circuit not downward across R1 and not upward across R2, but rather upward across R1 and downward across R2. And in fact, if we look at the two batteries, you can see that E2, having a value of 12 volts, is driving the direction of the current through each element, since it supplies greater voltage than E1. So the current through this loop, in fact, flows out of E2, up through R1, doesn't interact at all with this battery, but downward through R2. And so really what we have are two batteries which are in fact in parallel. And the net effect is that the current that does flow through the circuit flows in a fashion where from C to B to A to D. But it is not incorrect to have guessed the current to flow from B to C to D to A, since our initial guess works out using the loop rule to give us a value of current which is negative, therefore alerting us to the fact that our initial guess was not the correct guess. Let's view another problem, which is Kirchhoff's. Here we see that we've got two batteries and we have three resistors. We have multiple points along the two loops, the two smaller loops and the one larger loop that is described by this particular arrangement. And once again, our diagram has decided to guess for us the initial directions of the currents. So we'll go ahead and utilize the directions that they've given us here, but recognize that if we end up solving the currents and getting negative values, that the initial guess for the current was not correct. Okay, well, when we look over here, if I1 is indicated in this direction, it must be that I1 flows through R1 in this fashion here, making this the positive side and this the negative side. I3 flows downward, therefore when it gets to the resistor R3, it will flow in this direction, making this the positive end and this the negative end. I2 flows across here, and therefore it must be that I2, when it passed through R2, must have gone upward in this direction, meaning that this was the positive end and this was the negative end. So we make these notes since they will become very useful for us when we actually use the loop rule. But first, I'm going to go back to green. Let's write an expression for the junction rule. Use that as one of our equations. Notice that we have three unknowns, I1, I2, and I3. And according to the junction rule, the sum of what goes into the junction equals what comes out. Well, let's see what's going in. At the point C, I1 goes in, I2 goes in, but I3 comes out. So we have I1 plus I2 equals I3. That's our first equation. We need two more equations, and we're going to get these from the loop rule. So the question is, which loops are we going to use? Well, I know what you would say. Let's not use the big one, let's use the little ones. So now I'm going to ask you, would you like to go clockwise or counterclockwise at the top loop? And then the same question for the bottom loop. Take a couple of seconds to think about it. Well, since you didn't decide, I'm going to decide for you. Let's traverse the top loop in a clockwise fashion, starting with the battery E1, and the bottom loop in a counterclockwise fashion, starting with the battery E2. And I draw these so that when I apply the loop rule, I won't forget which way I'm traversing the loop and taking into account the drops and rises within that loop. So let's start with the top loop to give us an equation 2, and let's just come over here and lower this a little bit. And I'm going to start with the battery, the 14-volt battery. So because I am going from positive to negative, I have a minus 14, and again I leave out the unit, plus 6I1, since you can see that the direction of my loop takes me from the negative side of R1 to the positive side of R1. So I have a plus or potential rise. Minus 10, and here again, because I'm going from the positive terminal of the battery to the negative, minus 4I2, here from positive to negative across R2, equals 0. Let's clean this up a little bit, and we end up with minus 24 plus 6I1 minus 4I2 equals 0. That's my equation 2. And let me go ahead and underline my equation 1. Let's now go to the bottom loop. Here I have this in writing, although we can't quite see it, but I have a minus 10 volts plus 2I3 plus 6I1 equals 0. Well, let's see, is that correct? Plus 6I1. Now, what I want to do is I want to substitute, let's see, did I get this right? Minus 10 plus 2I3 plus 6I1 equals 0. I want to substitute I3 equals I2 plus I1 into this equation so that 2 and 3 will both have I1 and I2 terms in it. So let's proceed. Minus 10 plus 6I1, I'm just rewriting my I1, plus 2I2 plus 2I1 equals 0. See, because for my I3, I distributed the 2 times I2 plus 2 times I1. And I just happened to write my I1 term first because I wanted to be consistent with the order that I have equation 2 in. Well, let's clean this up a little bit. We have minus 10 plus 8I1 plus 2I2 equals 0. Now, what I want to do is eliminate one of the unknowns. And when I look at equation 2 and 3, the converted or the reduced equation 3, I notice that if I multiply equation 3 by a plus 2 and add it to equation 2, I will eliminate the unknown I2 and immediately get a value for I1. So let's proceed. Multiplying equation 3 by 2. So I'm going to take 3 and multiply by 2. And I'm going to get minus 20 plus 16I1 plus 4I2 equals 0. Now I'm going to take equation 3 and add it to equation 2. Well, let's go ahead and rewrite equation 2 here. Minus 24 plus 6i1 minus 4i2 equals 0. And you can see what's going to happen here when I add them. I get minus 44 plus 22i1 equals 0, since the i2's will drop out. Well, this gives me a value I1 equal to 2 amps. So I have now solved for my first unknown. To get my second unknown, I have several choices. Namely, I can take the value of I1 and substitute it either into equation 2 or equation 3, any equation which has I1 and another unknown. In this case, it will be I2. Let's go ahead and plug it into equation 2. Minus 24 plus 6 times 2 amps, what I just solved for, 6i1, minus 4i2 equals 0. Well, minus 24 volts plus 12 volts is minus 12 volts. Minus 4i2 equals 0, and I get a value of I2, which is equal to minus 3 amps. And you can see here that I2 was initially guessed incorrectly, since we end up obtaining a negative value. No harm done. We need our last unknown. To get I3, we note that I3 is the sum of I2 and I1, and so when we add up I2 and I1, we get a value of I3, which is minus 1 amp. Here again, the direction was guessed incorrectly, but we leave it at negative, except that we recognize that in fact, let's see if we can now get the color black. In fact, I2 should have been downward along R2, and I3 should have been left to right across R3, but I1 was chosen correctly. So in fact, I3 goes into the junction, I2 goes out of the junction, and I1 goes into the junction. So in other words, I1 goes in, I3 goes in, and I2 comes out. So in other words, the way the current is flowing through this circuit is along this direction if we consider the outer loop. But we leave our values there as negative since we applied the rules for the initially guessed directions. Next question. Here, the diagram didn't show, it came out corrupted, so I'm going to go ahead and just draw it for you. Question 8 says the ammeter below reads 2 amps. Find I1, I2, and the EMF 2. So this is what the diagram should look like. We have an R1 located here, which is 7 ohms. We have an E1 with a positive terminal and a negative terminal here, where E1 is equal to 15 volts. We next have a current which is shown to us as I3 passing through R3, which is equal to 5 ohms. And then in series with that branch is an ammeter, which is what we're being told the ammeter is measuring 2 amps, which must mean that the ammeter is measuring I3. And so we immediately determine the value of I3 without having done nothing more than noting where the ammeter has been placed. Now, R2 is given to us as 2 ohms, but EMF2 has yet to be determined. So let's go ahead and write down that I3 is 2 amps, since that will eliminate a lot of the headaches that we're going to have when we go to solve for the remaining 3 unknowns. Well, I didn't the only thing we have here is the direction of I3. I have not drawn out the directions of I1 or I2, even though on your original paper you have that. Let's go ahead and just randomly choose these directions as we apply the junction rule. Well, the first thing is that we want to decide the junction point. And let's go ahead, since I3 is drawn this way, and choose this to be our junction. And how about we say that I1 flows out of the junction, and so does I3, and I2 flows into the junction. Again, this is all a guess, since the only thing that we know is that I3 flows out of this point. Well, if we choose I1 in this direction, we're going to have an I1 such that when it flows through the resistor, this will be the positive end of the resistor, this will be the negative. I2 will be such that this will be the positive and this will be the negative. So let's go ahead and just draw an I2 here and an I1 here, so that when we traverse the loop, we'll remind ourselves which directions we chose for the current. Let me go ahead and select the green and write down our first equation, which is our junction rule. We see that I2 is equal to I3 plus I1. Since we know I3, we can write I2 equals 2 amps plus I1. And again, I leave out the unit just to eliminate the number of letters in our equations so that there is no mixing up of variables. Now, we need 2 more equations to solve for the remaining 2 unknowns, and so my question to you once again is, which way do you want to traverse the loops, and which loops do you want? Take 2 seconds to think it out. Okay, well, you do it your way and I will do it my way. My way will be to traverse the top loop clockwise, starting with the battery, and the bottom loop counterclockwise, starting with the battery. Well, let's go ahead and write down our loop rules, our potential rises and our potential drops. At the top loop, we have minus 15 plus I3 times R3, but our I3 is 2 amps, R3 is 5 ohms, and I'm leaving the units out, minus 7I1 equals 0. Well, this is 10 plus negative 15 gives us a negative 5 minus 7I1 equals 0. We immediately obtain a value for our unknown. I1 is 5 over negative 7, and in decimal form, this will be minus 0.714 amps. So we have our I1. It's a negative current, which means we must have chosen the direction incorrectly. We initially guessed it incorrectly. Well, that tells us that I2 from the junction rule is going to be equal to I2 is going to be I1 minus 0.794 plus 2. So let me just plug this into my calculator. 2 minus 0.714. I get a value of 1.29 or 286. Let's call it, well, we'll leave it as 2.86 so that we don't introduce rounding errors. So there's our I2. We come to the bottom loop, or the third loop, shall we say, or the third equation rather, minus E2 plus 2 times 5 again, plus 1.286 times 2 equals 0. Well, this right here gives us a value of 2.572. Added to 10 gives us an EMF, which is equal to 12.6 volts. We'll just round the 572 to 6. And we have now effectively obtained all of our unknowns, I1, I2, and the EMF 2. Last question is an RC circuit question. We are told that we have a circuit that contains a resistor of 8 e to the 5 ohms, a capacitance of 5 e to the minus 6 farads, and an EMF, oh goodness, not a little e, an EMF, somehow our EMF got translated to little e, an EMF of 12 volts. And we're asked to determine the time constant, the maximum charge, the charge and the current as a function of time, and the charge and the current 2 seconds after the switch is closed. Well, let's begin with the time constant. The time constant is the product of resistance times capacitance. When we take 8 e to the 5 ohms and we multiply it by 5 e to the minus 6 farads, we get a value of 4 seconds. Remember that the ohm farad is a unit of time. Well, now we've got our time constant. The next question is to find the maximum charge. Well, to get the maximum charge, we need the product of capacitance times the EMF. The capacitance is 5 e to the minus 6 farads. The EMF is 12 volts, and the product gives us 6 e to the minus 5 coulombs. So there's our Q max. Next, we're asked to determine the charge and the current as a function of time. Well, Q as a function of time equals Q max. And of course, well, let's go ahead and write it down here. We know now what the value of Q max is. And if you recall, it's 1 minus e to the minus t over RC. Well, let's go ahead and substitute to get the actual functional form. Q is 6 e to the minus 5 coulombs times 1 minus, and let's go ahead and, because we have a negative for the exponent, we can write this as 1 over e to the t over RC, which is 2. There's the function Q as a function of time. Next, current as a function of time is the maximum current, which we'll have to determine, times e to the minus t over RC. Well, the maximum current, using Ohm's law, will be equal to EMF over R. But we know that EMF is 12 volt. We know that R is 8 e to the 5 ohms, and we get a maximum value of 1.5 e to the minus 5 amps. Now we can write the functional form with numbers. I, as a function of time, equals 1.5 e to the minus 5 amps times, here again, we'll write 1 over e to the t over 4. The last thing we're asked to calculate is the charge on the capacitor 2 seconds after charging and the current through the circuit 2 seconds after charging. So Q of 2 is equal to 6e to the minus 5 coulomb times 1 minus 1 over e to the 1/2. 2 divided by 4 is a half. And when we plug these values in the calculator, we get 2.36 e to the minus 5 coulombs. So 2 seconds, or half a time constant, our capacitor has accumulated 2.36 e to the minus 5 coulombs of the possible total of 6e to the minus 5 coulombs. The current in the circuit has been reduced so that 1.5 e to the minus 5 amp, the maximum that it can have, times 1 over e to the 1/2, and that gives us a value of 9.1 e to the minus 6 amps. Well, this concludes the problem-solving session for Chapter 28. Until next time.